Stand on a quiet stretch of beach tonight. Look up. Somewhere above your head, sailing through the black, a small metal box about the size of a small car is still talking to us. That machine is called Voyager 1. It is older than almost every person alive, smaller than most school buses, and quieter than a whisper. Tonight, it is still phoning home from a part of space that no human being has ever visited, and what it is doing out there right now is going to change how you see the night sky. The channel that brings you stories like this stays free because of the quiet habit you are about to build. So before we fly out with Voyager, tap that join button, not because a stranger asked, but because every time this small machine sends one signal home, that signal is easier to find when there are real listeners on the other end of the feed. Picture the beach again. The waves roll in, the sky is clear. Above you, Voyager 1 is still there, and it is far enough away that the light leaving your face tonight will take almost a full day to catch it. That one fact should slow you down for a moment. We built a thing in 1977, and it is still working, and it is so far from us now that a single round trip of radio takes a day. The story of how it got there, and what it is doing out there right now, is also the story of the next 10 trillion years. And most people, even people who love space, have only ever heard the first chapter. Let us pull back now. To see why this matters, we need to step back to the way most of us were taught to think about Voyager 1 in school. We were taught that it was a finished mission. We were taught that it flew past Jupiter in 1979, that it swung past Saturn in 1980, that it took a famous family portrait of the planets, and that after that it slowly drifted away doing nothing in particular. We were taught that it is a relic, a goodbye card, a plaque with a whale song on it slowly tumbling through the dark. That is the picture most people carry in their heads. It is a kind picture. And the next act of this story is going to show that this kind picture is also a small one. Voyager 1 was launched on September 5, 1977, 16 days after its twin, Voyager 2. Both of them lifted off from Cape Canaveral on top of Titan rockets that were taller than a football field. The plan was simple. Take advantage of a rare alignment of the outer planets, swing from one world to the next using the gravity of each one like a slingshot, and see places up close that no one had ever really seen before. Voyager 1 flew past Jupiter and found active volcanoes on a moon called Io. It found that Io, a moon the size of our own, was the most volcanically active place in the whole solar system. Then it flew past Saturn and studied the rings in a way that shook every textbook that had come before. It found that the rings were not solid disks, as older astronomers had guessed, but thin, woven bands of ice and dust behaving more like a quiet fluid. The cameras were kept on long enough to do something strange. They turned around and looked back. They took one last famous picture of Earth seen from beyond Neptune. Carl Sagan called it the pale blue dot. From that far away, our entire planet looked like a single grain of dust caught in a beam of sun. The cameras were then turned off to save power for the long trip ahead. And right there, at that moment, like a door quietly closing, the popular story of Voyager 1 stopped. After that moment, the mission was, in the eyes of the press, over. Voyager 1 became a footnote. The public moved on to the space shuttle, then to the Mars rovers, then to the James Webb Space Telescope. The story that most people heard about Voyager 1 stopped in the 1980s, and that is the picture that has been carried for almost 40 years. Almost every popular book, every magazine feature, every television special treats Voyager 1 as a memory, a beautiful thing we launched and then walked away from. The thing is, no one asked Voyager 1 what it thought about that. Engineers at the Jet Propulsion Laboratory in Pasadena kept listening. The spacecraft has a big dish on its back, and it carries a small radio that runs on heat from a sealed drum of plutonium. That heat has been slowly turning into electricity for almost half a century. The radio signal it sends back is so faint by the time it reaches us that the giant antennas listening for it have to add up thousands of readings just to find it above the noise, but they keep adding them up. Almost every day since 1977, with very few exceptions, that small radio has talked. The notebooks the engineers keep have lines going back nearly 50 years. To give credit where it is due, the mission planners were careful from the very beginning. The current project manager is Suzanne Dodd, who has flown the Voyager missions from the Jet Propulsion Laboratory for many years. The science lead for plasma work has long been Don Gurnett at the University of Iowa, whose name we will see again because his work is what changed the story. Voyager 1 was designed with a backup for every backup. Its flight computer runs on 8,000 bits of memory, less than what is inside a single photo taken on your phone. Most of the software was written in a programming language so old that the original engineers who wrote it have long since retired into their 70s and 80s. The whole probe weighs about 825 kilograms, about what a small delivery van weighs with no packages. It is, in every way, a small and humble machine, and the people who built it understood that. For most of its life, we have treated Voyager 1 as a goodbye, but we are about to see that this is a small part of a much larger story. Before this becomes about the science, it begins with something simpler. Write down, right now in the comments, the exact moment you first believed that Voyager 1 had already finished its real job. Was it a textbook in 4th grade? Was it a teacher who said the last picture was the pale blue dot? Was it a TV special from the 1990s? Tell the story of when you first heard that beautiful pale blue dot line and walked away believing the mission was done. We read every comment like this. They shape the next video we make, and that next video is going to go even deeper into this. What we have just taken for granted turns out to be a small part of a larger story. Voyager 1 is not done. It is not a relic. It is, in a quiet way, the most active probe we have ever built, and the only one we have ever placed between the stars. Then, in August of 2012, something happened that no broadcast had ever told anyone about. Voyager 1 crossed a boundary in space that no spacecraft had crossed before. The boundary has a name. It is called the heliopause. Think of our sun as a small campfire. The heliopause is the place where the wind from that campfire finally dies down. Beyond the heliopause is the wind of the rest of the galaxy. That place is officially called interstellar space, and Voyager 1 drifted into it. The trip is still happening. The probe has not come back. It is still out there right now. Until that year, scientists had only guessed what that place sounded like. They had models drawn on whiteboards. They had theories about plasma waves. They had 30 years of careful work done by people like Don Gurnett, who had helped put a small instrument called the plasma wave system on Voyager 1 back in the 1970s, and who had been listening through it ever since. In September of 2013, Gurnett and his team published a paper in the journal Science that confirmed, with measurements, that Voyager 1 had crossed fully out of the sun's wind and into interstellar space. The data behind the confirmation came from a tiny change in the way electrons around the spacecraft vibrated. A small change in squeal. That small change told the world we had a probe, finally, between the stars. Months later, the tone of the data changed again. The same plasma instrument began picking up a kind of low, steady hum. It was a faint, constant tone, like a single deep note on a piano, ringing all the way through the dark. In May of 2021, a Cornell-led team, with Stella Koch-Acker as the lead author, published a paper in the journal Nature Astronomy. They wrote that the hum was steady, persistent, and could be tracked by Voyager 1 for years into the future. Their analysis showed that what we had been hearing was a sustained signal from interstellar plasma, a sound that no probe had ever recorded before, because no probe had ever sat long enough in that part of space to hear it. Voyager is sitting there, quietly recording the breathing of another part of the galaxy. The same way a doctor can listen to a chest with a stethoscope, the plasma wave instrument is listening to the chest of our local galactic neighborhood. The expected picture had been that outside the heliopause, space would be emptier, quieter, and simpler. What Voyager 1 actually found was that interstellar space carries its own steady hum, a low vibration at roughly a few kilohertz, that the spacecraft can hear when nothing else is happening around it. The surprise was not the volume. The surprise was the persistence. The signal kept going. For years, the probe kept recording the same quiet note. And that note is teaching us what the space between stars is actually made of. It is worth slowing down here. The expected picture had been that outside the sun's wind, the plasma would be steady and uniform. What Voyager 1 actually found was something stranger. The interstellar medium is not a still pool. It carries long, organized filaments of plasma, sometimes hundreds of light years in length, and the probe has flown through enough of them to draw a rough map of where they bend. Imagine crossing a quiet ocean and finding hidden rivers running through it. That is roughly what Voyager 1 has shown us about interstellar space. We have also learned that the magnetic field just outside the heliopause is stronger and more tilted than older models predicted. The textbooks from before 2012 are quietly going out of date, one chapter at a time. We have also learned that even the people studying this do not entirely agree yet. Some scientists, including members of Gurnet's group at Iowa, think the local interstellar magnetic field is steadier and more single in direction than we used to think. Others, including people at the Johns Hopkins Applied Physics Laboratory, think it is patchier and stranger than the first clean models had suggested. There is a real, healthy disagreement about what those filaments actually are and what they say about how stars and galaxies trade material over time. Voyager 1 is the only machine we have in that part of space, and it is going to keep teaching us for years. Soon after that discovery, in late 2023, the spacecraft started misbehaving. Its flight data system, which is a small computer that packages the readings before they are sent home in radio form, began sending back garbage. Something had broken. Something that no one on Earth could touch with a hand. The probe was already more than 15 billion miles away. The light speed delay one way was already more than 22 hours. The team at JPL spent 5 months, from November 2023 to April 2024, working on a fix that had to be relayed in tiny patches of code through the Deep Space Network, the chain of giant radio dishes that talks to our farthest spacecraft. They finally moved the affected code into a different memory location because the original chip could not be repaired at that distance. In April of 2024, NPR and Forbes both reported that Voyager 1 was once again making sense. It was 47 years old at that point. It had been sick, gently, and it had survived, gently. In parallel, the power story has been quietly catching up with the probe. Voyager 1 runs on heat from a small, sealed drum of plutonium-238. The drum is a radioisotope thermoelectric generator. When the probe launched in 1977, that drum produced about 470 watts of electrical power. Today, it produces about 220 watts. The natural decay of the plutonium is a steady countdown. The spacecraft loses roughly 4 extra watts every year, and there is no way to plug it in. To stay alive, the mission team has been turning instruments off, one by one, in a slow and careful retreat that mirrors the long, patient journey. In February of 2025, the team switched off the cosmic ray subsystem, a key instrument for measuring high-energy particles from far away. In March of 2025, NASA confirmed that the low-energy charged particle instrument would be shut down near the end of that same year. By April of 2026, according to the most recent mission blog from NASA, only 2 science instruments remain powered on. Each one is being chosen for the same reason you would choose which bulbs to leave on in a house during a long storm. The magnetometer, which measures the invisible magnetic field around the probe 8 times a second, and the plasma wave instrument, which first confirmed the interstellar crossing, are running together. These are the same 2 instruments that the Gurnet group at Iowa and the Cornell-led team rely on. Their data is being archived in raw form so that decades from now, when better tools exist, scientists can reanalyze the same numbers with sharper eyes. If the story we have just walked through is right, then the way we think about Voyager 1 is going to quietly shift for anyone who ever looks up. For most of a lifetime, we treated Voyager as a finished postcard. Now we know it is a working observatory, the only observatory we have ever placed in interstellar space. And we know it is fading, but not yet gone. This story has stopped being about one machine and has become about how long a small thing can keep doing useful work in the deep. Share this video today with one specific person. Send it to a friend who still thinks space exploration quietly ended after the space shuttle. Send it to a parent or grandparent who told you when you were young that the last picture Voyager ever took was the one with the pale blue dot. They need to see this part of the story in their own time, because a quiet share from you is exactly the kind of carry that keeps stories like this alive past year 1 of when they first saw them. What changes because of all this? First, our view of where Voyager 1 actually is changes with hard numbers and dates. As of this year, 2026, the probe is sitting at about 172.59 astronomical units from Earth, according to the most recent update from NASA's Voyager mission page. An astronomical unit is the distance from the Sun to Earth, about 93 million miles, so 172 of those means Voyager 1 is more than 25.8 billion kilometers away. On November 18, 2026, at 2:16 in the morning Pacific Time, Voyager 1 will pass the mark of exactly 1 light day from Earth. That means the signal it sends back will take a full 24 hours to arrive at the Deep Space Network antennas, and our reply, even moving at the speed of light, will take another full day to get back to the probe. One round trip will then take 2 days, just to say hello. Second, the science timeline ahead changes. With only 2 instruments still squeezing out data, the focus has narrowed to the questions those instruments are best at answering. The magnetometer is tracking variations in the magnetic field that lies between the stars. The plasma wave instrument is listening for any shift in the steady hum. Both feed into ongoing work at the University of Iowa and Cornell. Both are being archived so that a graduate student in 2080 can open the same numbers again, with better tools, and find new things. This is a long science project, built to outlive the people who started it. Third, the horizon changes. Voyager 1 is heading in the rough direction of the constellation Ophiuchus. Its path will eventually carry it near a small star called Gliese 445, also known as AC plus 793888, in roughly 40,000 years, give or take a few centuries based on updated parallax measurements. That is the next closest star-like object along its path. Its drift will then carry it through the outer fringe of the Oort cloud, the loose bubble of icy bodies that surrounds our Sun far beyond Pluto. Even a quick crossing of that cloud alone could take another 20,000 years, because the cloud is so wide that our fastest probes will spend more time crossing it than modern humans have existed. After that, for billions and trillions of years more, the probe will simply orbit the center of the Milky Way, along with the rest of our local group, almost untouched by anything, longer than the current age of the universe. Fourth, the meaning for everyday life changes. The probe has been traveling for almost 49 years. During that time, it has crossed the orbits of Uranus and Neptune. Voyager 2 has done the same, and has now also crossed into interstellar space itself. Voyager 1 is still the farthest human object ever made. The Voyager interstellar mission, as NASA officially named it, has been extended not once but several times, because the science returns are still real. We built the probe for a 4-year mission to the outer planets. It has now been running for nearly 50. The ratio is hard to feel, so let us borrow one you can feel. Put it against a kettle. A kettle takes about 3 minutes to boil. Voyager 1 has been traveling for almost 49 years, and during that time it has crossed the orbit of Uranus. If a single second of kettle time were 1 month of Voyager travel, the kettle would have to stay on for more than 140 years to match what Voyager 1 has done so far. There is no domestic comparison that fits cleanly, so we have to borrow a planetary one. Think of the Sun. The Sun has been burning for about 4.6 billion years. If the Sun's life were compressed into one Earth day, the entire Voyager 1 mission so far would fit inside the last second. And in that single second, the probe crossed out of the Sun's wind and into the void. What you should look for next is small and patient. Look for NASA updates about the next instrument switch-off. Look for papers from Gurnet's group at the University of Iowa. Look for news releases from the Voyager team at JPL, where project managers like Suzanne Dodd still hold weekly meetings about a spacecraft most people on Earth have forgotten. Look for the long-term Oort cloud studies being prepared for the European Space Agency's upcoming Comet Interceptor mission, which will borrow some of the Voyager navigation lessons. Look for young researchers, including graduate students just finishing their first year of PhD work, who have asked to be allowed to reanalyze the archived Voyager data using newer machine learning tools. If you happen to be outside on a clear winter night and you look toward the constellation Ophiuchus, you are looking in the rough direction that Voyager 1 is sailing. You will not see it. It is too small. But knowing the direction is a quiet kind of seeing. There is also one unresolved question worth holding in your mind. Where exactly is the boundary between our Sun's wind and the interstellar medium? The heliopause was drawn in older textbooks as a clean line. Voyager 1 is teaching us that it is more like a slow froth, with thick bands and thin gaps that vary depending on where the Sun is in its 11-year activity cycle. That question will keep physicists busy for decades, because there is only one probe, in only one place, measuring as it goes. A few years from now, probably before the year 2030, the last working instrument on Voyager 1 will be switched off. The plutonium will still be warm. The radio will still whisper its tiny carrier wave. But nothing useful will be riding that carrier back home. Engineers say they will keep listening for the carrier itself, the silent tone that simply says the probe is still there, for as long as the Deep Space Network can hear it. After that, Voyager 1 will go quiet and sail on for trillions more. And here is what is coming next. There will be a small crowd at JPL when the very last science instrument on Voyager 1 goes dark, probably in the late 2020s. There will be news articles that say goodbye again, a second time. There will be a final meeting of a long team that has been meeting every single week for almost half a century, with the same agenda item more or less, the same small machine, the same slow countdown. There will be children who were not yet born when this probe was launched, who will hear the word Voyager for the first time from a teacher, maybe in 2036 or 2042, and who will ask the same question we all asked. Why did we send it? The answer will keep shifting in their hands, the way a coin keeps catching different light. In the meantime, somewhere out there the probe is still drifting. The magnetometer is still measuring. The plasma wave instrument is still listening. The gold-plated record, with its whale song and its greetings in 55 human languages, is still bolted to the side of the spacecraft, slowly heading out of the solar system. In about 40,000 years, it will pass near that small red star in the constellation Camelopardalis. After that, it will pass through the outer edge of our Oort cloud over the next 20,000 years. And then, for trillions of years, it will sail around the center of our galaxy in a long, slow loop, almost untouched by anything we know. Picture the beach one more time just before we close. Picture the small, distant machine, still warm, still sending. Picture the kettle at home, finally clicking off after boiling quietly for longer than most families have been alive. Picture one signal, on a tiny radio, still traveling outward from Earth toward a probe that has already gone past almost everything we know. Picture the next 10 trillion years, all of them, holding that small object inside. That is Voyager 1. That is right now. And that is what we are going to keep watching, for as long as it lets us. Bookmark this page. Come back in a month and watch this again. By then, Gurnet's team, or a JPL engineer at her desk on a long Thursday, or a fresh undergraduate somewhere who has just opened one of those archived data files for the very first time, will have found something new in the same numbers. And we will be here to walk you through it, the way we always have, for as long as you keep tuning in.